We're working through solving equations. There are many different ways to solve equations, and there are ones that you find every solution. We did a lot of those yesterday. So the answer would be things like a pi upon 3 plus 2k pi, you know, that kind of one. There was a few where we just got the answers as decimals, right? The answer was 0.123. And what I'm going to show you today is some more solving equations, but in particular, I'm going to show you how to solve an equation like this. And what we're being given is this equation, and we're being asked to find when is y equal to 0, right? So we're basically trying to find the values of t that make that 0. And it's a pretty horrible equation. It's one of those damped oscillation ones. And what you're going to do is you're going to do it graphically using Desmos. So I'm going to take you over now to Desmos and show you what I did. I just typed in the function, right? Now, I guess I could type in y equals 0, but isn't y equals 0 just the x-axis? So I don't need to type that in because I know what it is. And when you look at all these vertical lines, that's very distracting. So I'm going to go over here and I'm going to change the x values. And the x values are going to start at 0, right? And I'm going to finish at 4. Now, doesn't that curve look much more understandable now that you can see it with a better window? So just because you type something into Desmos doesn't mean that, you know, you should stick to the window it gives you, right? Now I am looking for when is the y coordinate 0. So I'm looking for that guy, x equals 0, that guy, 0.5, that guy, which is 1, 0. And now I've got a problem. There is one more, that guy. And if I kept looking, I could get others. For instance, that guy, and that guy. You see them all? But they only wanted the first 4 answers.
So why isn't it those other dots?
Oh, they count as well.
Okay.
That one, right? So that's the first one, x equals 0. The second place is at x equals 0.5. The third place, that's nothing to do with us, so I wish that would go away. The third place is here at 1, 0. The next place is not that one, actually. It should be that one, there, 1.5. So we are only putting in where the value is 0. That one there isn't 0. Desmos tells you where things cross the x-axis. They tell you where things cross the y-axis. They also tell you when it's the top of a hill or the bottom of a valley. And do you see that tiny little valley there? See that dot there? Can you imagine it? Almost no hill at all, but there's a baby hill, a very tiny bump. But we're only interested in when the y value is 0. So first answer is there. Let's click that to go away. Click that one to go away. And click that. Can I make it go away? Right. Make that one my second one. That one's my third one. That one doesn't have 0, but that one does. So what have I got? 1 answer, 2 answers, 3 answers. There we go. They only wanted the first 4, and that is it. So plug in the equation. In this case, do it equals 0. Suppose you had to solve the equation, this ugly thing equals 1. So I would just type in y equals 1. And wouldn't I be looking for that value of x and this value of x? And so if they wanted to know when did this equation equals 1, so if that's what you're trying to solve, your answer would be x equals 0.02 and 0.339. I'm pretty sure it never has any other answer. Are we good with that question? So Desmos, as long as you type it in and play about with the windows, things should make sense. So we're now moving on to set 2. There are 3 sections on equations here. 3. That's a lot of equations. The next one that we're going to solve, again, it's going to be graphically, is y equals sine x. I know you can't see it, but we're trying to find out when sine x is equal to 0.6. And they want the first 1, 2, 3, 4, 5 answers. Right, I best show you what the question is. So we're being asked to solve the equation. When is sine x equal to 0.6? And you're only allowed to choose x's in the range plus to minus 3 pi, right? And there might be 2 answers in that range, there might be 12 answers. And our job is to find all the solutions within this range. Now you can do that with Desmos, but you have to put in a little bit of work. It's not, you know, given to you right off the bat. So let me kill these guys off first. So I'm going to type in y equals sine x. And I want to find when is it equal to 0.6. So I put in y equals 0.6. Now, when you look at this guy, can you see that there's an answer there, right? And there's an answer here. And there's lots of other answers. If I zoom out, can you see there's an infinite number of them. But they only want answers from -3 pi to pi. So I'm going to go here. I'm going to do a little what I call curly bracket. The curly bracket is to the left of the entry button. And I'm going to put to -3 pi for pi, less than or equal to x, less than or equal to 3 pi. Put a little curly bracket. Oh, click out of that. And curly bracket again. Well, actually, save some time. I'll just copy that. And then I can paste it. And there we go. Now I'm going to go into my window because that's very hard to see. And I'm going to change the y values to, I think, probably something like -2 to 2. That's the wrong one I just managed to choose there, isn't it? So y values I wanted. So I want this guy to be -2 to 2. Yeah. Okay, would you agree that I can see pretty clearly now all the guys I want? Now, if you click on the guy, you see how WebAssign will tell you its coordinates, and we want to know only the x coordinates of where that happened. So -5.64, that guy, I guess I'll click on this one, right? If I got it, yeah, that guy, that guy, that guy, that guy, and finally that guy. So by telling WebAssign I only want -3 pi, can't I find all the numbers we want? And that 1, 2, 3, 4, 5, those 6 numbers are the ones that you should be putting into WebAssign as your answer. And here's a little thing you have to be a little bit careful about when you're doing WebAssign. It says it wants it, how does it phrase it again? Something like, yes, a comma separated list. So the phrase it uses.
I have a question.
Yes.
So it asks for 4 decimal places, but Desmos only gives it to 3.
Oh, I think you can make Desmos do more than 3. Let me, well, I'll tell you, I'll do 2 things. Let me get the comma separated thing, then I'll figure out how we can make Desmos be just a little bit more accurate for us. So it asks us to do a comma separated list. And they're a big box. And all that means is you type the first guy in. Now you're right, they do have them to 4 decimal places. So there's the first one. And then you type in the second one, right? And so on, right? So I'm now going to go back to Desmos and see if we can make it give a more accurate answer. I know it should be able to do it. Let's see if I can make it. Okay, I've lost my Desmos picture. Oh, here we are. I got it back. Try under here. Let's just display, that didn't do any good. Try here.
I can't see your screen.
Oh, I'm just playing about with it right now. I'll show you. I'm trying to figure out where it would be, but I guess you can see me playing about with it while I do that. I went in here hoping that it would have a setting that would allow me to do that. But, well, it might. What would that be? No, I doubt that would be it. Try this. Does that help? That just converts it to a table. I'm sure it can do it. Just haven't figured out how to make it happen yet. It probably is here. And then you click on it, maybe double click on it. Well, little experiment. This is what I would do. I would say Desmos, how to increase accuracy. And somebody will have figured out how to do that. That's what I'm hoping anyway. There we are. Controlling for the number of decimal places. Right? Can you see that heading? No? I'm just in a screen here. Let me see if you can see it. Yeah, can you see it now? So here we go. Somebody got a little problem. I'm trying to do this. Is there a way to do it? Yeah, it looks like you have to do it through programming. Okay, I don't want to spend any more time. I've still got a feeling it's doable, but just in case it's not, I'll show you a backup.
Maybe I forget what the site's called, GeoGebra. That might be more accurate.
Oh, there's other programs out there. Let me just show you the other less pretty way of doing that same thing then. So you make sure your calculator is in radians, you hit y equals, and you basically do the same thing that I just did, which is sine x, close brackets, and then what was it, 0.6? No, let's clear that, 0.6. I'll do my window from -3 pi to +3 pi. And then I should be able to just zoom 0, which is zoom to fit. Okay, and so the guys I want are here, 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 here. So if you then go second calc and you choose option number 5, intersection, if I move this little cursor around so I can see where it is, here we are. All right, it's a little low car. Do you see it driving? Here we go. There, I'm going to drive my car to the first one on the left-hand side, press enter. And then I'm going to just drive it a little bit along the straight line, maybe not as much as that. See here, enter, guess, hit enter. There's the answer to more accuracy than you need. So that's a backup plan if Desmos doesn't do it accurate. You see, you can do in your calculator. I mean, that works as well, doesn't it? It's just not as pretty, that's all. And that is the end of numerical versions of solving equations using calculator and or Desmos. And then we move to basically that was question 1, but also question 2 is very similar. To show you a kind of combination of the two. We know that there is an infinite number of solutions to any trig equation that has this form. So this is one I'm doing. Now, if you imagine me doing that on my calculator, which I certainly could, but it would look something like this, right? And 0.57 would be a horizontal line. And can you imagine that there's going to be an infinite number of solutions, right, forever? Great. So on your calculator, I'll do it this way because it's also quicker. I'm going to do y equals sine x again, and I'll change this to 0. I've committed 57. What are we interested in? I'm interested in the answers from 0 to 2 pi. Typically, that's the range I would look at. And then I'll do zoom to fit. There we go. And I'm just interested right now in those two solutions, because that doesn't matter and that doesn't matter, right? So I've got two solutions. This first one, this one here, you go second calc, you choose option 5, which is intersection. You drive your little car until he is near the guy you want. I'll do. Enter. Drive your little car so he's near the guy. Enter. Guess. Enter. And the answer I get is 0.6065. Let's say we want it to 4 decimal places. Right. Now, how do I get the second one? Well, you just go back and do second calc again. You choose option 5 again. You drive your little car, but this time you drive it so that it's near that one. You press enter. You drive your little car somewhere close to it. Press enter. And the second answer I get is 2.5351 to 4 decimal places. We did yesterday examples where these were nice numbers, right? Pi upon 3 and pi upon 4. Can you remember what you would add on to get all the other infinite solutions? It was the same thing every time for a sine function. What did you add on?
2k pi.
2k pi. So that would represent every solution in the universe, not just those two, but the others that go this way. And if you take away 2k pi, because k is allowed to be negative numbers, you get all the answers that are over here. Okay. So far, so good. Now, still on numerical. The difference here is that it's not x, it's 2x, and that's going to become important at this stage here. So we have the sine of 2x is 0.4. So I'll go to my calculator. I'll change this guy into the sine of 2x. And I'll make this guy 0.8. I'll keep my window the same. But I'm only looking for 2 answers, so it doesn't matter if there's more. And then I'll do zoom 0, which is zoom to fit. And the 2 answers that I'm interested in are going to be the first 2 answers. These 2. I don't care about these 2 or the ones that come later, because this bit here is going to take care of those. So the 2 answers using the calculator. That's going to be my first one. That's going to be my second. So here goes. Same routine as before. Second calc, choice number 5. Okay, that's pretty, the writing's in the way, but that's pretty close to the one I want. And so is that. So first guy I get is about 0.463, let's say 2 decimal places. And then I'll do it one more time to get the second one, which is all I need. And it's over there somewhere. And the other one is about 1.107, right? But what I've found, right, is the x values, right? This 2k pi thing, when your function is y equals sine x, it's 2k pi. When it's y equals sine of 2x, this gets altered. The general version of this is x equals, I'll call it the answer, plus k times the period. So what is the period of the sine of 2x? What is the period of the sine of 2x?
1.
Yeah, 1
Pi.
pi. Yeah. So it's 0.463, not 2k pi, but just 1k pi. So that's just one more thing to add to our problems, haven't it? We get two answers, right? And then if you want to see all the answers in the universe, you have to add some multiple of pi. And when it's sine and cosines in the ones we've done before, isn't it 2k pi? But that's just a special case. And if you were doing that, you would probably call this the period k, right? Try that again. Bit of a cheat. Suppose I'm doing a cosine and it's 3x and it's equal to 0.7. I'm not going to solve it. I'm going to pretend I know the answer. Let's pretend I know the answer is 0.123. How many k do you add? Well, you add whatever the period is, k. Now, this is a 3 cosine of 3x. What is the period for the cosine of 3x? Did it a couple of weeks back. Well, isn't it 2 pi divided by 3? So your answer would be 0.123, not plus 2 pi k, not even plus pi k, but plus 2/3 pi k. So if you're solving an equation and this guy here is not x, then you have to bear in mind that the multiple of k that you use to generate all the answers that come after has a general formula, the period of this guy, k. So if its period is 2 pi, 2 pi k. If it's only 1 pi, 1 pi k. If it's 2/3 pi, 2/3 pi k. And you only end up saying a limited number of any one example of what we've just done. So let's leave decimals for a while and return to solutions that you can use your unit circle on. So this is a version of this is question 3. And we have the sine of theta is negative root over 2 over 2. And you're being asked to write down what theta is. And they do that comma separated list thing. So I'll show you what that is in a minute. Theta then, right, is any point whose y coordinate, any angle I should say, whose y coordinate is negative root 2 over 2. Well, if I use my unit circle and I look for an angle whose y coordinate is negative root 2 upon 2, can you find, there's two of them, can you find those two guys for me? What angle in radians in the unit circle do you have a y coordinate of negative root 2 upon 2? I didn't think that was a tricky question. I can see 2. Can anybody see them?
Pi over 4 and 3 pi over 4.
Oh, let's see. Well, you're close. It's the
Oh, it's
negative.
negative. Sorry. 5 pi over 4 and 7 pi over 4.
Great. You'll see them now. See that one there? And the other one's over here. Now, this question wants all the answers, right? What is the period of sine theta? Just a normal sine theta. What's its period?
2 pi.
And so, period K. And how does it work in your homework? The comma separated list just wants you to type that guy in, comma, that guy in. I know we're jumping around a lot, but that's just what these do, right? You got one question that was Desmos, another that was the calculator, ones where you had to, figure out what the period was, one where the period was 2 pi, because that's just a basic trig function period.
So is there no way to combine those two equations into one, technically?
You could, if you wanted to do multiples of a half pi, but we're not going to ask you to do that.
Okay, so will WebAssign just ask us for 2 equations?
Yeah, well, it asks you for a comma separated list, so you just write all the answers down in that box.
Oh, okay.
Yeah, yesterday they actually gave you 2 separate boxes just to be different. And today you just get one box, 2 answers if there's 2 with a comma between them. Right. The next version is question 6. And it's 2 cos squared theta, take away a cosine theta, take away a 1 equals 0. And I'm getting really strong déjà vus on this one. We either did one exactly like this or at least very similar to this yesterday. This expression with cos squares and cosines in it is technically a quadratic. If it helps you to understand how it factors, think of the cosine as being a b. So how would this fella factor? And we did one almost like it, if not this one yesterday.
Isn't it 2 cosine x plus 1 and then cosine x minus 1?
Yeah, there we go. You're right. And from the first factor, we are looking for values that make this 0, which means that we're looking for when is the 2 cosine of theta 1, which in turn, we are looking for when is the cosine negative a half, and these answers are in the unit circle. And so I'm going to get theta equals, and there are going to be 2 of them. And I'm looking for when is the x coordinate equal to a half. And when I look for when is the x coordinate equal to a half, I get pi upon 3. And the other place when the x coordinate is a half is 5/3 pi. So far, so good. Now, this question again wants all the infinite answers, so they want that plus 2 pi k kind of thing. In this case, isn't it a single cosine, right? It's a cosine of theta. And so we can just do the 2 pi k. And then we'll look at this one. And we want to find out for what angles is this 0. So that becomes when is the cosine 1. And that ends up being when is the x coordinate equal to 1. And the x coordinate is equal to 1. Actually, only in one place, isn't it? 0. And since we want the infinite answers, and this is also a cosine of a single theta, we get that. So when you're looking at this question and you're writing all your answers in, do they want them in any order? No, I don't think they want any order, so I'm just going to write them in the order that I found them. You wouldn't say 0 plus something. 2 pi k is enough. You see the variety on different kinds of trig equations. One where you had to factor, one where you're just given a single one, others where you had to use graphing calculator or Desmos. And this particular one, you also had to do factoring. And this one, you had to adjust what multiple of k you used. Every question is really, you don't know what you're going to get until you see it. Last one of this type is going to be question 8. And that's the end of this section. This one's a little bit different. You're given the formula that the sine of theta 1 over the sine of theta 2 is equal to V1 over V2. I'll actually show you what that looks like. If a beam of light hits a surface like glass or water, it gets deflected from the vertical, which is that dotted line going here. And the angle of incidence, which just means the angle that it hits this angle up here, the water at, it gets deflected very often, and it gets deflected like this. So it doesn't go straight through in a straight line, it gets bent. And the second angle, theta 2, is called this guy. And V1 and V2 are the speed of light through that medium. So it's light in air and then light in water, they go at different speeds because of the density of the medium. So that's just the theory behind that, but this is the guy that matters. So you are going to be given a question at the bottom, and it says the following: that theta 1 was 65 degrees. That V1 is 1, and that V2, well, they give you a table, and it depends on what it's passing through. In this particular one, it's going to be water. And so when it's water, this number is 1.33. And you are being asked to find the other angle. So you're given this formula, you're told these 3 numbers, and you're being asked to find the angle theta 2. So I would begin by rewriting the formula here. That's 1. That's 1.33. That's the sine of 65 degrees. And this guy is the sine theta 2. So I know 3 out of the 4. What kind of algebra technique do you use to solve an equation that looks like that? I'm kind of giving a hint with the way I'm moving my fingers.
You'd multiply, cross multiply.
Yeah, so 1 times this guy gets you sine theta 2, and going this way you get 1.33 times the sine of 65 degrees. Now this particular situation, there's only one answer, so we have to be aware that there's just one answer. So 1.33 times the sine of Yeah, 65. Let me check something. Yep. Make sure you're in degrees. So 1.33 times 65 degrees. And I get, that doesn't make sense. Is it degrees or radians? Is degrees. Okay. It helps when you read the question. I got the 1 and the 1.3 mixed up. So it's going to be 1.3 times this guy is equal to the sine of 65. And so this fellow is going to be sine of 65 divided by 1.3. Yeah, that makes better. And the reason I knew that was the answer was 1, and you can't get 1 for a sine. So sine of 65 divided by 1.33. And I am looking at almost done. If the sine is 0.68, how do I get the missing angle?
You take the sine inverse.
Yeah. On my calculator, inverse sine of 0.6814, and it's about 42.95 degrees. I'll give you a few moments to finish that off. And just loading up the last trig equations. And this one is not 7.5. I've done that one, haven't I? No, it's a new one. Okay. And, oh, it's section 7.5, solving trig equations. All right, we'll get this one done and we will have completed what we need to be able to do in those ones. Of course, being the last one, they are going to be really ugly if they didn't think the earlier ones were. I have a sine of x plus 2 sine of x cosine of x equals 0. And let me redo this question. There we go. Pause for a minute. Let me share something with you because I'm not very good at scanning. And that's a classic example of it. This here is actually the next line of working. You all know I wear glasses. What you might not know is that I'm virtually blind in my left eye. I was born that way. And anybody who's got a very similar situation to me knows what I'm talking about. I have very major problems with depth perception, right? I can't easily judge how far away things are. And it's quite funny at times. I do things like I miss door handles. And sometimes I bang into doors with my hand because I misjudge the distance. Another problem I have is scanning. So when I go over here and I look at the question on my other screen and I look at this one, I'm looking at line 3, and then when I go back, I'm looking at line 5. So that's exactly what happened here. This was the question. When I looked to scan, I saw this, which was the first line of working, instead of that. So if you're wondering why I do that, going for the sympathy factor. I just can't scan well. It's hard for me. You know, if you do reading, I sometimes skim to the next line. So let's pretend you don't know what that is, because that is going to be the next line. We are trying to solve an equation that has a mixture of sine x and sine 2x in it. None of the techniques that we've used so far are going to work. We do not want in this question to get decimal answers. If there was, I would just plug that into decimals. We want to get exact answers. And what we're going to use is we're going to use various trig identities or formulas that you know. And since I've crossed that out, you probably can't see it anymore. But does anybody know the formula for the sine of 2x? It's called the double angle formula.
2 sine x times cosine x.
And if you're trying to solve an equation, would you agree it probably have a good idea to make everybody x's, right? You can't have 2 x's here and x's there when you're dealing with trig. Now that it's done this way, can't I pull out sine x as a common factor? So now I can factor it. And once I've got to that stage, basically we are done as far as this question is concerned. Because won't sine x be 0 and solve? And won't the other one be 1 plus 2 cosine x equals 0? And normally you would go to the end and solve for these. But in this question, you just stop there. That's all they wanted you to do. To find out what each piece would have to be equal to solve it. So you're not really solving it, but writing down what you would need to do to be able to solve it. Here's a version of question 2. This time I'll try and scan a bit better. It's a cosine of 2 theta. And it's going to be 7 times the sine of theta, take away 3. And this one we're going to solve all the way to the end. I'm going to remind you of some guys here. We've just done the sine of 2 theta. It's 2 sine theta cosine theta. We are about to change that double angle. There are in fact 3 versions for the cosine of 2 theta. Does anybody remember any one of the 3 equations for the cosine of 2 theta? There are 3 of them, any one of them.
One minus 2 sine squared theta.
Nailed it, perfect. Pushing your luck a little bit, but does anybody know any of the other 2? Pretty good you got one, but I'd be even happy if there was somebody who knew the second one. I'll tell you the third one. Has cos squared in it. That's the last clue I'm giving you. Something with cos squared in it.
Two cos square a minus 1.
Yeah. Okay. We cool with that? Does it look right? Let's check it out. we assume this one is correct, then cos squared theta, take away sine squared, isn't sine squared 1 minus cos squared? So that would get you cos squared theta, take away 1, plus a cos squared theta. Collecting the cos squares together, you nailed it. If you can remember just one of these, couldn't you figure out the other two by doing something similar to what I just did here? Right. So let's put a big box around these guys. And I have to rewrite this fella now. Oh, this guy over here. I have to figure out, or we have to figure out, what to change the cosine of 2 theta into. And I have three choices. I could change it into that guy, I could change it into this guy, or I could change it into this guy. But only one of those three is actually going to play well with this equation. Only one of those three. The one with the sines in it, the one with the cosines in it, or the one with both in it.
Would it be
Which
the top one?
Agreed. What's your reasoning?
Well, because it just has 2 sine squared in it, and the others don't even have sine squared.
Yeah. So you kind of want everything to be the same. That tends to work well. So I'm doing the 1 take away 2 sine squared theta. I think in this case, it's probably easier to add 2 sine squared theta to both sides and to subtract a 1 from both sides. Okay, so I now have an equation with nothing but variations of sine and sine squared equal to 0. And I know we haven't done a lot of these, but hopefully every time we come up with a new one, it'll become a little bit easier to remember. This is a quadratic in sine theta. Because it says 2 sine theta squared, I know that it's going to have a 2 sine theta on one of them, and the other one's going to be a sine theta. Since this is the number -4, aren't I going to have combinations like +2 and -2 or +4 and -1, right? But only one of those combinations is actually going to generate a +7 sine x, a +7 sine theta in the middle. Any takers for that one? What number, what version of -4 here and here is going to generate a +7 sine theta when you FOIL it all back out?
Would it be a -1 in the first parentheses and then a +4 in the second?
And it would, and you nailed it. Does that seem reasonable? Can you check it and FOIL it out in yourself in your head? It does work, right? So we now have that, which means that we now have to deal with finding when is 2 sine theta take away 1 equals 0, if at all. And the other choice is when, if at all, does that equal 0. Let's take this one first. If this was going to be true, and you subtract 4 from both sides, wouldn't sine theta have to be the number -4? Would you agree that's impossible? Doesn't the sine only go big to 1 and down the other side to -1? Isn't that the range that the sine theta goes, right? 1 to -1. So that is impossible, and it's okay. We haven't done anything wrong. It just means that you'll get no solutions from it. That's okay. Now, this fella, if you add 1 to both sides, and then you divide both sides by 2, oops, wrong piece of paper, we get,
Pi over 6 and 5 pi over 6.
check it out, pi upon 6, nailed it, and 5 pi upon 6. Since they want the infinite answers, it's going to be pi upon 6 plus somebody, right? And 5, 6 pi, right? Plus somebody. Who you want to go for?
would be pi upon 6 plus 2 k pi.
And I'm just writing it as 2 pi k now.
Yeah.
Can you see the period is 2 pi? Why is it
Yep.
2 pi? Because it's a sine theta, right? And that tends to be the predominant version, right? So can you imagine putting these two with a comma beside them and you are done. And that is the end of that particular question too. Being the final version of the trig, nothing is going to be particularly obvious, right? You're going to have to work on every single one. But one of the themes that happens a lot is, don't you want everybody to be sines or everybody to be cosines? What you don't want is a 2 theta and a single theta, or sines and cosines like we have here. And I'm going to put this guy over here to the side for a minute. And I'm going to write down some more identities. That's probably the first identity we ever write down. But it can be rearranged. Cos squared theta can be called 1 minus sine squared theta. And sine squared theta can be called 1 take away cos squared theta. So they kind of all belong together, don't they? They're just different versions of the same information. Now, let's look at this guy. Can't really do much with a 1. I don't think there's anything obvious I can do with a single cosine theta. So my brain is saying, okay, that's the only guy in town that I have any chance of changing into something else. And I have to figure out what I could change it into. And I'm going to look over here and I'm going to say, well, that's not much use. Nope, nope.
That'd be 2 minus 2 cosine squared.
So it's going to be 2 lots, just like you said. I'm just putting in an extra line of that guy. And so it's going to be 2 take away 2 cosine thetas, take away a cosine theta equals 1. And if that wasn't bad enough, there's a little hiccup at the end we have to deal with. So let's figure it out. If what I'm going to do next is I'm basically going to take away 1 from both sides and stick the 1 on this end. So if you take 1 away from both sides, that becomes 1. And I've picked that 1 up and transferred it to the end, right? So it's still on the left-hand side, so it's still plus 1. Now, I do not want to, nobody should want to factor this guy. So I'm going to multiply both sides by -1. Would you agree that's an improvement to what it looked like a minute ago? Ah, we have seen this guy for the 4th time. Can you see a quadratic in this time cosines? And if it's a quadratic, it'll factor. Two cos squared plus a cosine minus 1. Since it's 2 cos squareds, I'm pretty sure it's going to have that. Now all I need to do is figure out what the numbers are. Well, the 2 numbers that I'm going to put here and here have to multiply together to give me -1. And they have to work in such a way that when I FOIL it out, I get a single plus cosine theta. What's the combination that's going to make that happen?
Would it be -1 plus 1? So it'd be -1 in the first box and
Yeah.
plus 1. Yeah.
Yeah, that's how I interpret it. Would you agree with that, guys? Does that look good? FOIL it out and check it. It works. Which means we now have to figure out, when is this equal to 0? Well, that becomes when 2 cosine theta equals 1. And that happens when, when the cosine of theta, write that again, when the cosine of theta is a half. Time for a unit circle. The Cosine is a half. There's an x coordinate of a half. So that's going to be pi upon 3. And when's it also a half? It's going to be a half down here, isn't it? So the other one is going to be at 5/3. And there's some stuff to tag on, but I'm going to leave it for a minute. And this one is, when does that equal 0? Well, that equals 0 when the cosine of theta is -1. And if I find that, it ends up only happening in one location, and that's when it's pi. Now, this question wants to know, what does this question want to know? Oh, it wants to find all of them again. The final answer, right, had cosine thetas in it. Isn't the period of a cosine theta 2 pi? And we're finished. The vast majority of questions that we do, don't you end up with sine thetas and cosine thetas? And because of that, it's going to be 2 pi k. Now and again, you might have a sine 2 theta or a tan 2 theta or something. Then you have to do that little, period times k trick. But most of the time, it's 2 pi k, because most of the time you end up with sines and cosines. Are we good? The more you do these, the better you get. I mean, there's no substitute for just practice. Get one last one. And this last one is going to involve changing the plus 2 pi k thing. And I know that because it's that guy. There is no trig identity for the cosine of 3 theta, right? There's cosine of 2 thetas, right? But there isn't a cosine of 3 theta. So I'm not going to change it. I'm actually going to leave this guy alone. And I'm going to try and solve it in the usual way. Well, when is the cosine equal to a half? Well, the thing inside is that guy. And when is it equal to a half? It's equal to half at pi upon 3. And it's also equal to a half at 5/3 pi. And that makes theta divide both sides by 3, pi upon 9. And this makes theta divide both sides by 3, 5 upon 9. So far, so good. Now, they want the infinite answers. This is not going to be 2 pi k. If it was cosine theta equals a half, this would have been 2 pi k. But when this is a multiple, 2 theta, 3 theta, things like that, we need to use the period. Okay, let's try this one. What is the period of the cosine of 3 theta?
2 pi over 3.
You nailed it. So guess what? 2/3 pi k, 2/3 pi k. Do you see how that little hiccup introduces it? And basically, you've now got all the answers you want. Well, thank you for hanging in what must be, it gets a little bit, yeah, it gets boring for some people, but it certainly gets a bit monotonous if not, because we're just doing lots of different things and we're trying to, juggle all these balls in the air. But it's good that you've lasted this long. Tomorrow, we'll finish them, and that will be the end of trig equations.